Okay, we'll wait for a few minutes for others to join.
Sir? Sir?
Yes, Santosh, any doubts?
No. Last, what you did say, sir, just now?
I just said that we'll wait for a few minutes for others to join, then we'll start.
Okay.
Okay, let us start. Welcome to the week 8 tutorial for the course IC Engines and Gas Turbine. I hope everyone is regular to the lecture videos. We are more than half of the journey of the syllabus. So, yes, Santosh, any query you have?
No, sir. I don't have any query.
Okay. So,
Sir, one doubt, how to contact in between this?
so there are two ways. There is a Google form discussion form which you get by the NPTEL team in the email. You can contact for the doubts and everything. Other ways on my, if you have any doubts and related to the session, you can comment on my video which is uploaded on YouTube. I'll try to reply there. Okay. Or also you can search my name on the social media and you can contact me, connect with me.
Social media means
LinkedIn
Instagram.
or accounts. It's all upon. Okay.
LinkedIn and Instagram.
Whichever you find. Okay.
Okay. You are. What's your name in LinkedIn? Varnit Kapoor.
Yeah. So, but mostly try to you can use the comment section of the videos as well. No issues.
Okay.
Okay. So in the last tutorial, we almost finished up with the IC engine. We were doing the testing of the Williams line method and the motoring test. Okay, and we completed with the combustion in the CI engine. Now today we will finish up with the one test which was left, that is Morse-Keys test, which is eventually used for multi-cylinder engines, and then we will move forward to the gas turbines.
Okay.
Let me share my screen. Meanwhile, you can keep on note if you don't have any doubts. I hope my screen is visible.
Yeah, sir. Visible.
Visible. Okay. All right. So let's start with the Morse key test. So we did the motoring test, which was eventually for a single cylinder. Morse key test is basically conducted for multi-cylinder engine. Morse.
Bluetooth mode.
Can you keep it yourself on mute, Santosh, if you don't have any doubt?
What's up?
I'm saying, can you keep yourself on mute if you don't have any doubts? There is a background
Okay,
noise.
okay,
Yeah, thank you.
okay, okay.
So it is used for a multi-cylinder and it can be used for both CI and SI engines. For multi-cylinder and both for
So,
SI and CI engines. Okay. Yes, any doubts?
Can you please raise up your volume? I can't.
Okay, just hold on. Is my volume clear now? It's better? Just hold on, it's on our now. Is it better?
Yeah.
Okay, thank you. And it is used to obtain the indicated power without having any measuring devices. Okay, it is used. Can you keep yourself on mute? Obtain indicated power without any. Santosh, can you keep yourself on mute?
I was muted.
You are not on mute. Actually, background noise is coming. Without any measuring device. Okay. All right. So what happens here? What do we do? So let me make a figure of four. Let us say four cylinder IC engine. So we have four cylinders. Okay. Four stroke, four cylinder IC engine. Okay. All have the positions of pistons at some random positions. Let us say one is at compression, maybe one is at expansion. Okay. And all are connected through a shaft. Okay. Crankshaft, which provides which provides the power to the engine. Okay, this is a connecting rod. This is a schematic diagram. All of these four are connected, and the order of firing can be different. So what we actually do when all the four cylinders are working. Okay, so when all the four cylinders are working, what happens at that point of time? The engine will be producing brake power on the wheels. That is the four times of the brake power, as well as the friction is also involved here. So friction will be four times of the friction. So what do we do in this test is basically we short one by one each cylinder and check how much of the brake power is produced. Friction power is going to be constant at each point of time, and you will subtract from the friction power the brake power. You will get your indicated power. Okay. So what is the indicated power? Whatever the power that is produced inside the piston cylinder arrangement. And brake power is the power that is produced at the output or the wheels of the vehicle, wheel drum or wheels of the vehicle. We have seen this definitions in very detail. So what do we do? So let us say we have a heading that is brake power, we have a heading that is friction power, and we have a heading, and sum of this both is equal to indicated power. Okay. First scenario is that when all the cylinders are fired. Okay. All another pen. All cylinders are fired. So that means all the cylinders are working. Okay. Am I audible, Santosh, clearly? So that will be 4 times of the
You are audible.
okay. So 4 times of the brake power. Okay. So let us say 100 kilowatt of a, let's for example say that 100 kilowatt of energy is being power has been produced. Okay. And friction power will be 4 times of F. Okay. So this will give me the net indicated power of the system that I don't know for sure currently. When I say that I shot the first cylinder, that is my first cylinder is not having any spark or combustion taking place. Okay, in my first cylinder. So let us name cylinder one by one. 1, 2, 3, and 4. Okay. If I say I cylinder one is cylinder one not fired. Okay. So what will happen? Only 3 cylinders are going to produce some power. So that will be 3 times of the brake power. But friction will always be there. Piston will be continuously, even if you don't provide any heat in this scenario. And the first cylinder, rest all the cylinders are experiencing the power stroke. But if this is not experiencing any power stroke, still the piston is moving because of the presence of the inertia. And if the piston is moving, the friction will always be there. Okay. So friction is also always going to be there, and that will always be 4 times of F. Okay. Let us say that these 3 cylinders, cylinder 2, 3, and 4, which were fired, are producing 80 kilowatts of energy. Okay. Let us say these are producing 80 kilowatts of energy. So how much will be my indicated power by the first cylinder, which has been stopped? So indicated power will be, if you subtract both of them, so what you will get, this and this is going to cancel out, friction power. 4 brake power minus brake power is basically your 4 brake power was 100 kilowatt, 3 brake power was, because of 3 cylinders, 80 kilowatt, so it will be 20 kilowatt, and that will be the indicated power because of the first cylinder. Okay, if you wouldn't have shot or you wouldn't have stopped the supply or firing of the first cylinder, you would have got this 20 kilowatt from the first cylinder. Okay, I'll directly write now instead of in this detail format. So the indicated power will be 100 minus 80, that is 20 kilowatts, and that will be indicated power because of the first cylinder. Okay, indicated power of the first cylinder. Now if I say, if my cylinder 1 is again fired, but 2 is not fired this time in sequence, cylinder 2 not fired, rest other being fired, combustion is taking place in rest all the other, again it will be 3 times of the brake power. But if the first one is not fired, let us say they produces 75 kilowatt together, the second one is not fired, then they produce 75 kilowatt of brake power, and friction will always be there. Then again it will be from this equation you will subtract this equation. Okay, so when all were fired and when second was not fired, so you will get your brake power indicated power from the first one. So that will be 100 minus 75, so that is 25 kilowatt of indicated power by the second cylinder. Indicated power by the second cylinder. All right, now you got to know that if I stop or don't fire or combust the fuel inside a second cylinder, it would have produced 25 kilowatt of the indicated power. If I say now my cylinder 3 is not fired, cylinder 3 not fired. So we are not using any measuring device like we were using tachometer, dynamometer in the motoring test. Okay. But here we are not measuring using any measuring device. Just by firing, stopping the firing, we are able to get the indicated power. So let us say the brake power which was being produced by the other 3 cylinders, let us say it is 70 kilowatts. Okay. Okay. And friction power will be again 4 times of F. So again, if you subtract the first equation with the third equation, you will get 100 minus 70, that is 30 kilowatts of indicated power from the third cylinder. Okay. Let us say now 4 cylinder is 4 not fired. Okay. So here again 3 brake power, but let us say it is producing 60 kilowatt plus 4 times of friction. So that will be 100 minus 60. So that is 40 kilowatts of indicated power by the fourth. So how we can get the net indicated power? Indicated power of 1 plus 2 plus 3 and plus 4. So what was the indicated power provided to the system? That is our 4-stroke 4-cylinder IC engine. So net indicated power will be indicated power because of 1 plus indicated power because of 2 plus indicated power because of 3 plus indicated power because of 4. So this is 20, 25, 20 plus 25 plus 30 plus 40. So this will be how much?
110,
Hmm?
110 kilowatt. 110 kilowatt.
90, 90, 105, 90, 115, right?
115, 45, 20 plus 25, 45,
70,
45 plus 25, 75 plus 40, yeah, sorry, 115, double 115, 150.
115. Okay, so it will be 115 kilowatt. Okay, that is your net indicated power because of the 4 cylinders. Okay, now you tell me, if I say which cylinder is best in 1, 2, 3 and 4, which one is best? By seeing the indicated powers, can you tell me that which cylinder will be best and which
Sir,
should
can
not
you,
be stopped?
sir?
I am asking, can you tell me by seeing that which cylinder is the best, which should not be stopped? So I think if we
Can you
see
scroll
that,
back? Can
so if
you
we
scroll
see,
back, sir?
huh,
No,
so
no, sorry. Upwards. Scroll upwards. No, sir. Not that was. So, 1 minute. BP plus IP equal to IP in it.
so if I say my first
Hello.
cylinder is producing 20 kilowatts, second is producing
I
25,
have.
third is producing
I
30,
know, sir.
and fourth is
I'm
producing
asking.
40.
Hello.
Yes, Santosh.
You are audible, sir. I am audible.
Yes, yes, you are audible.
No, I am asking how can you show the cylinder one not fire?
How I
Scroll back. How 100 minus 80? 100 is percentage, sir.
100 minus what?
100 represent 100 minus 80.
So that is 20.
Okay. How the 80 will be substituted? From
This
which
is
value the
I'm taking just for an example that if four were producing 100, let's say one was not fired, so three producing 80. Second is not fired, it is producing 75. Okay, so you can get that brake powers from the motoring test. Okay, for each cylinder, we have seen the motoring
okay,
test. So my question is, we are calculating the indicated power. So indicated power
okay,
for multi-cylinder scenario is that the best cylinder will be in the cylinder number 4, and we should never ever stop this cylinder because it is producing maximum amount of indicated power in this scenario. Okay,
okay,
so we should say that best cylinder is indicated with the indicated power 4. So, and what will be the mechanical efficiency now? That is brake power to that of indicated power. And what is brake
into
power?
100.
100 by
100.
115 into 100. Okay, so that will be your mechanical efficiency. Okay. And to be noted here, fourth cylinder produces maximum indicated power and shouldn't be stopped. Okay, this is the best cylinder now. All right. Is it clear or any doubts? This was the Morse key test.
Yeah, first test.
Now let's come to the gas turbine. So we are almost finished up with the IC engines. Let me
Okay.
gas turbines. the topic gas turbines. So what is an engine basically? Engine is basically a work producing device which converts one form of energy into another useful form of energy. Okay, that is converting the low grade form of energy into high grade form of energy. Low grade is your heat, high grade is your work. Okay, and it is a mechanical device which converts one form of energy into a useful form of energy. There are two types of engines. Basically, first one is the internal combustion engine, and another is your external combustion engine. So internal combustion engine we have seen in the last 7 tutorials in very detail. Where we have discussed the Otto cycle, dual cycle, diesel cycle, the actual working and the ideal or theoretical working. We have seen the combustion processes happening in each of them. Then how the fuel parameters affect knocking, and then finally the testing scenarios and a lot of numericals in between. So that was an IC engine. So in case of IC engine, the what happens basically, the product of the combustion, that is the fuel itself, is the working fluid, and it is producing an output over the wheels. So combustion and expansion both were taking inside a piston and cylinder that is in a same location. Okay. Whereas an external combustion engine is basically where the products of the combustion are transferring their heat to the another working fluid, and they are used for producing some useful output. So if you see in the turbines, what happens? Your coal is being burned somewhere. Okay. That energy of heat is used to superheat the, when you are talking about the gas turbine, you are superheating the liquid which is present there. Okay. Which is used for producing the useful output. And these are happening, the burning of the fuel is happening at some other place, and transfer of heat is happening because of the presence of heat exchangers to the working fluid, that is liquid, that is your water or whatever liquid you are having. And the location is totally different in both the scenarios. So let me write. So turbines or gas turbines are the part of external combustion engines. Okay. So what is an engine? I'll again write. It is a mechanical device which converts one form of energy into useful form of energy. Okay. How many types of engines are there? The first one is IC engines, that is your internal combustion. Here, in case of IC engine, product of combustion itself is working fluid. So the air fuel mixture which is in an Otto cycle is getting combustion, that is getting fired itself, as well it is also a working fluid, okay, which eventually converts into exhaust gases. Is a working fluid and produces the output, that is your work done. Combustion and expansion take place at same location. Okay. Wherein then external combustion engine, in case of EC engines, products of combustion transfer their heat to another working fluid, and which is used for producing some useful output. Combustion and expansion. Here the combustion and expansion takes place at different location. Okay. So very important points to highlight here is that the IC engine same location, in AC engine different location. Okay. Now what are the advantages of gas turbine over the IC engines? We have to see advantages of, there are advantages as well as disadvantages. So let us talk about the advantages. So for short form, I'll write gas turbine as GT over IC. So first advantages, it is a much simpler mechanism because you are combusting the fuel somewhere else compared to the IC engine, which is a complex scenario where you have a lot of things in a single location. Combustion is taking place separately, so it's a simple mechanism. Here, high speeds can be developed due to the rotary engine presence of the rotary engines. Okay. We will study the rotary compressor and rotary engines as well to the later part. The balancing is also easy here, whereas the balancing scenario in the IC engine is very quite complicated. Okay. And the another is it is quite compact. By compact, I mean weight to the power ratio is less. Okay. So you produce more power compared to the weight you have. The compact means that. Wherein an IC engine cannot produce that much amount of power. It can run a vehicle, but it cannot run a whole, produce so heavy motors or large amount of supply of the electricity. Okay. So the first advantage is simple mechanism. Second, easy balancing. Third, high speeds can be developed. Due to rotary engine, these engines you can also see in your aircrafts. The large turbines are there in the aircraft when you have, if you might have traveled in the aeroplane or a flight, you can see the bigger on the wings, quite huge engines are there. Those are gas turbines only. So if you see that, those are rotary engines, they rotate at a very high speeds. And the other one is the compactness. What do I mean by compact? That is weight to power ratio is less. So you can easily understand that why IC engine is not used in a aeroplane. Okay. So IC engine can only pull a vehicle, a normal automobile vehicle, car, bus, truck. Okay, but it cannot be used to run a aeroplane. Whereas if the presence of the rotary engine make it a bit high speed scenarios, and it can be used in the form of the compactness that you can carry so high amount of load, passengers as well as the machinery of the self weight of the machine itself, as well as the luggage or extra cargo which you have. So IC engines can produce 5 to 10 megawatts, whereas EC engines can produce thousands of megawatts. Okay, I'll write here example. IC engines can produce 5 to 10 megawatts of power, and EC engines can produce near around 1000 megawatts of power. Okay. Now, if it has advantage, definitely it will have disadvantages as well. So first disadvantage is that there is a compressor which has been used. I'll explain the working step by step, but let me write first the advantages and disadvantages. The compressor which has been used in the gas turbine is used to handle the gaseous phase of the working fluid. Okay, if your working fluid is water, you have to handle a, or any of the fluid is there if you have a refrigerant kind of scenarios. So you have to handle that gaseous phase of that fluid, which is not negligible. Okay, so it consumes some amount of work and significant amount of work. So that is why you cannot write the net work is just the difference of the heats. Okay, heat supplied and heat rejected. But here the net work will be work done as an output that has been achieved at the turbine minus the work which you have provided to the compressor. Although it will be less, but it cannot be neglected. It is significantly high. Okay, so let me write the disadvantages. And by easy balancing here, I mean that there is a balancing which is involving the rotational as well as reciprocation. So when you will see in your theory of machine the rotary engines, you will see that there is a 2/3 of revolutions take place, reciprocation take place, and full one weightage is given to the rotation. Okay. First one is the compressor used. The compressor used in gas turbine handling gaseous phases of working fluid which is not negligible in comparison to turbines. Therefore, net work output reduces, and therefore efficiency is less than that of, therefore efficiency of gas turbine is less than efficiency of IC engines. Okay. What do I mean? That the net work will be work produced by the turbine minus work produced by the compressor. So compressor is a work absorbing device, whereas turbine is a work producing device. So eventually, both are open system devices. Both are open system devices. So what can be the work for an open system device? We know that it is negative of VDP from thermodynamics. Okay. Negative of VDP, that is change in the pressure into the volume, the specific volume of that gas. Okay. So it will be, the compressor will be significantly high, and the net work produced by the turbine is it's going to decrease. Whereas if you say in IC engines, we have never written what is the work during the compression. We have always said that whatever is the area under the graph is the net work produced, and it is just equivalent to the net heat interaction based on the first law of the thermodynamics. Okay. All right. Next, So should also write this point, that is negative of V of gas into change in pressure, and this can't be neglected. Can't be neglected. Okay. So whole cycle itself is a closed cycle, but each process is going to be an open system process because every component is in the ambient. Okay. Next is high speed reduction gears are required as the value of the centrifugal forces are high. Okay. So if you have such a high speed available at the output of the shaft, you don't want that much amount of high speed. You want some reduction to happen. Otherwise, because of the presence of so much of amount of high speed, the forces will be very high, centrifugal forces, and they can break down the blades of the turbine. So high speed reduction. Second, high speed reduction gears are required. Are required as the value of centrifugal forces are high. What do I mean by that? What is my form? What is the expression for centrifugal force? That is mr omega square. Okay, mr omega square, and omega can be written in terms of n also. That is revolution per minute instead of radian per second. We can say that Fc is directly proportional to the revolution per minute. So if speed is very high, then the force is going to be extremely high. That is square of that of the RPM of that turbine. Next disadvantage is that high heat resistance material are required for the gas turbines because they are subjected to very high temperature for continuously working of long time. Okay. And so if you drive a vehicle maximum for 2 hours, 3 hours, and you give a rest. Okay. Then and that too not every day, suppose 2 hours, 3 hours, and with the break, because a human can drive for long 8 hours as well, but they will eventually hurt their body itself. So that's why it's required to have a break. And with the presence of that break, the vehicle is also getting the break. So the temperature is eventually going to cool down, okay, with time. But the gas turbines are working in the power plants and they have to continuously produce the electricity. Okay. So they run for almost 24 hours, 365 days with minor lag maintenance periods and eventually working at such high temperatures. So the blades needs to be of a very high resistant materials so that they shouldn't get damaged eventually with time. Okay. So let us say the third point is high heat resistant material like nickel, which has a high creep resistance. Okay. So we saw that nickel alloy in the spark plug also. Okay. So you can see the nickel is having a various advantages at multiple places. Nickel, which has high creep resistance, are required for gas turbine because they are subjected to high temperature. Continuously for long period of time. Okay. All right. So these are the disadvantages. One point I want to highlight here is that the exhaust temperature of the IC engine is much higher compared to the gas turbine. Okay. Because in IC engine, everything is happening at the same place. So you are having a possibility of multiple hotspots. And if hotspots are there for a SI engine, spark ignition, then there is a presence of end charge combustions to take place, and that can create a knocking scenarios, which is not favorable. If you connect like this, then you will be able to understand in a much better way. Okay. Now, how many types of gas turbines are there? First is an open cycle gas turbine. Another is a closed cycle gas turbine, which eventually leads us to a Brayton cycle. Okay. Brayton cycle. So let us write the types of gas turbine. If at any point my voice doesn't come, please immediately point me out. Or if my screen doesn't share properly. Types of gas turbine. The first one is open cycle gas turbine. So let us discuss this in detail. So in this case, every cycle, inside every cycle from compression to heat exchange to expansion or power to exhaust, a fresh charge is introduced. What do I mean? A fresh uh, air mixture is used to produce the work output from the turbine. So what do I mean? Let me write. In this case, in every cycle, a fresh charge is introduced. So what are the components here? The first component is your compressor. So for the work absorbing device, we like a converging section of a rotation. Then we have combustion chamber where the fuel is, or the coal, whatever your fuel is, it's being burnt, and you get the heat which is being supplied here. Heat which gets supplied here. Then you have a turbine, and for work producing device, you always make a diverging section kind of schematic diagram. And finally, it is a sent to the exhaust. And from here, the fuel is entered into the, not fuel, basically the air mixture, which is at the atmosphere in pressure, is getting entered into the system. So let me write the arrows. So from this to this, this is your compressor, and this is your turbine. At point 1, the air at atmospheric pressure is being introduced. Air at atmospheric pressure. Then it get compressed. Then it get, because air is your working fluid here, which get compressed, and that is exchanging the heat from the combustion chamber because of the presence of the heat exchangers. That air get a very high temperature from there. So this is a state 2 after being compressed. This is your state 3 after getting heated to a higher temperature. And finally, that superheated state of the gas is used to run the, it strikes over the blades, and that is used to run the turbine and produce a power output. And this, both of them, right, the compressor as well as the turbine are connected to the same working shaft. Okay, same shaft. So let me remove this right now. Okay, and this is your compressor. This is your turbine. And finally, this is your situation number 4, where it is being exhausted to the atmosphere. Exhaust to, and again in the next cycle, a fresh air mixture is taken at the atmospheric pressure. Exhaust to atmosphere. Okay. So how we will make the pressure, volume, and temperature entropy plot for these? Let us do. Pressure and volume. First process is compression. So from atmospheric scenario, P atmosphere, from stage 1, if we say this is your stage 1, the volume is there already. It get compressed, isentropic compression. Okay. The process will be, the first process will be isentropic compression. Second is constant pressure heat addition. So let me write the process first instead of making the graph. Process 1, 1 to 2 is isentropic compression. Second is process 2 to 3. Constant pressure heat addition, because the device is inside at the ambient pressure, so it will be a constant pressure heat addition from the ambient scenarios, and at the same pressure from the output of the compressor, the heat is being added to the through the heat exchanger by burning of the fuel. Constant pressure heat addition. Process 3 to 4, isentropic expansion. That is the work producing scenario from the turbine. Expansion. And there won't be 4 to 1, because again the same air is not being used or recirculated inside the cylinder. A fresh air mixture is used, that as I wrote in the open cycle gas turbine, in every case, in every cycle a fresh charge is introduced. So let me make pressure, volume. So this is at P atmosphere, let us say. So again, first is 1 to 2 is an isentropic compression. So from 1 to 2, isentropic compression. Then 2 to 3 is a heat addition at constant pressure. So at the same pressure, the heat is going to add, and 3 to 4 is your isentropic expansion, coming back to the atmospheric pressure. Okay, as I wrote here, exhaust to the atmosphere at the 4th point. Okay. But there won't be any 4 to 1. There won't be 4 to 1. All right. Similarly, temperature entropy, because a fresh air-filled mixture has been introduced, that's why. Same air mixture is not used. Next is temperature entropy. So 1 to 2 is an isentropic. So what do we mean by isentropic? That adiabatic and constant entropy. So there won't be any entropy change. So from 1 to 2, it will be a vertical line. So 1 to 2, the vertical line from here to here. 1 to 2 isentropic at constant entropy. Then 2 to 3 is a heat addition. So at constant pressure. So let me write here heat addition at constant pressure. At constant pressure. So what is the slope of temperature entropy plot for a constant pressure, it is basically temperature to that of Cp, specific heat constant at constant pressure. We have seen this dT by ds is equal to T by Cp for a constant pressure process, and it is less than the constant volume process. The slope is lesser. So 2 to 3 is your heat addition at constant pressure. So 3 is your scenario where again temperature is going to rise. Pressure and temperature both are going to rise. So this is your 2 to 3. And 4 to 1 is again isentropic scenario, and it is exhaust. So this will be your fourth point. That is okay. So this is your cycle. Okay. Any doubts in this? Okay. So this was an open cycle gas turbine. Any doubts? Santosh, Ravindran?
No, sir, no, sir. No doubt.
Not.
No doubt.
Okay. Now let's come to the closed cycle gas turbine. The second one. So in this case of closed cycle, same working fluid is recirculated again and again. So let me draw the schematic diagram of this. So again, there will be a compressor that is connected to a combustion chamber that is connected to a turbine that is connected to an exhaust, which is again connected to a heat exchanger. HE is your heat exchanger. Okay. Cycle will be this. The arrows inside the cycle are very important. This is again your compressor. This is your turbine. Okay. Here the heat is being added, and here the heat is being rejected, QR. Okay. And both are again connected to the same shaft. Okay. So only there will be another change in the above graphs, that here and here the line will be added. So let us make the graphs once again. This is your pressure, volume. So again we start with P atmosphere. Do you think I should write P atmosphere here or not? What do you think, Santosh or Ratish? Should I write P atmosphere? Should I start with P atmosphere here? No, right? No P atmosphere, because the same fuel, same air or working fluid is used again and again. We are not introducing the fresh air fuel mixture from P atmosphere. Okay? So it won't start from P atmosphere this time. This will start from some pressure, that is P1, let us say. So again, 1 to 2 is your isentropic compression. Isentropic compression. 2 to 3 is your heat addition at constant pressure. 3 to 4 is your isentropic expansion, and 4 to 1 is your, I think I didn't make a good diagram. Okay, so this is 1, this is 2, this is 3, and this is 4. So here the heat is being added, Q supplied, and heat is being rejected at constant pressure. Okay, so here let us say this is P1 equal to P4, and here P2 is equal to P3. Okay, the pressure is. So here this is heat exchanger. Even combustion chamber is also called as heat exchanger. Let us say it is heat exchanger 1 and this is heat exchanger 2. Okay, and this is an exhaust process. Let me use some another color, not this. So additional is your exhaust process. And from here is being again recirculated back. Okay, all right, so this was a pressure volume plot, and similarly there will be a temperature entropy plot. Temperature entropy, so 1 to 2 is again isentropic compression, 2 to 3 is in heat addition at constant pressure, 3 to 4 is isentropic expansion, and 4 to 1 is your constant pressure heat rejection. That is why slopes are, they are parallel to each other. So 1, 2, 3, 4, and finally exhaust process. Okay, so highest temperature scenario will be at point number 3 in the cycle, and highest pressure is at point 2 and 3, same. So we will introduce one term, that is RP, that is your pressure ratio. Okay, where in the IC engine we used to have a compression ratio as well as expansion ratio, but here we are introducing a term that is called as pressure ratio. So pressure ratio is that, and whenever I am talking about the ratios, I have told that is higher to lower value. Okay. So pressure ratio is nothing but P higher to that of P lower, and higher pressure is at 2 and 3 and lower is at 1 and 4. Okay. All right. Now, what are the advantages of closed gas turbine over the open cycle? Okay, closed cycle to that of open cycle. Just give me a minute, I'll be back. Okay. Am I audible? Can anyone confirm? Hello. Santosh, am I audible? Ritesh, if not, please confirm me so that we can start. Okay, thank you. The next is advantages of closed cycle gas turbine. Over open cycle. So the first one is in closed cycle, if you are using a one of the working fluid, you can take different working fluids. Whereas in an open cycle, you have to deal with air only. Okay, because variety of working fluid can have a different combustion properties. Okay, and products of the combustion also don't enter the turbine. Next is there can be a better thermal efficiency when you are operating between maximum and minimum temperature limits, because the value specific heat constant values Cp will be different for different working fluids, or gamma will be different. So better working fluids can be used like argons and heliums, which have higher gamma values. And also it can operate even below atmospheric pressure. Okay. So when I'm talking about the closed cycle gas turbine, I can take it below the atmospheric pressure as well. But in open cycle gas turbine, you have to be within the start with the atmospheric pressure. Okay, you cannot go much below than that. So let me write. First is wide variety of fuel can be used because products of combustion doesn't enter turbine. Second, better thermal efficiency can be obtained between same maximum and minimum temperature limits by using different fuel that is imply Cp or gamma value to be higher. Okay, so these can be like argon, helium, having these are monatomic gases. So gamma is higher for them, 1.67 for a monatomic gas compared to a diatomic or triatomic gases. Okay, and why I'm saying, I'll write just the efficiency formula first, thermal efficiency formula for a Brayton cycle. That is nothing but 1 minus 1 by pressure ratio to that of gamma minus 1 by gamma. I'll derive this, don't worry. But if you observe, higher the gamma, lower this whole value and higher the efficiency. Okay. Similarly, if you see for the Otto cycle also, if I say Otto in IC engine, that was 1 minus compression ratio to the power of gamma minus 1. Okay. You again have a higher gamma, whole will be higher, overall will be lesser, and efficiency will be higher. That is why you can have different either gas or some another fuel to burn. Okay. So next advantage is that it can operate even below the atmospheric pressure. operate even below atmospheric pressure. Okay. So if you are going more below the atmospheric pressure, that means, so I say this was my atmospheric pressure in this graph. So the area under the graph will be this much only. But if I'm going much below the atmospheric pressure, that means still here, then my area under the graph is going to increase. So by that, I can increase the net work output. And by that, I mean to say I can increase the efficiency, because efficiency is nothing but the net work output to that of net heat supplied. Okay. This implies that is efficiency of Brayton cycle increases since area under curve increases. Okay. Now again, if there are some advantages, so it will also come up with some disadvantages as well. So disadvantage is that there is a requirement of a coolant which is used to cool down the turbine exhaust before entering the compressor. Whereas in open cycle gas turbine, atmosphere itself acts as a source and sink scenarios. Okay, so act as a sink. But if you want to go with the closed cycle gas turbines,
Sir,
the fuel which is, just hold on, just the fuel which is being traveling inside a gas turbine has to be cooled down when it is at a very high temperature. Yes, Santosh.
sir, doubt. View the working medium of gas turbine is gas. What type of gas is used in open type gas turbine, sir?
What type of
Hot
take?
gas. I don't know. Sorry, what?
Your question is what type of gases we can.
Yeah. I am asking what type of gas is used in gas
That is
turbine.
what I've written here, na, that we try to have a monatomic gases for a closed system scenario whose gamma is higher and they can
Okay.
produce more efficiency. But
Gamma represents.
gamma represents the polytropic index. Okay.
Okay.
So
Okay.
higher the gamma, higher the efficiency will be. But for our derivation point of view, we are assuming that we are dealing with air for currently. Okay. We will deal in our theory that is working fluid is air. I'll derive the derivation, don't worry. Now coming up to the disadvantages, as I told that there is a requirement of a coolant to lower down the temperature. Next is that if there is a closed system scenario, there is a possibility that leak proofing is very difficult. So when you are going much below the atmospheric pressure, then I said that if this was my atmospheric pressure and I'm going much below the atmospheric pressure, there is a chances that from the heat exchanger, the atmospheric air can enter into the pipes. Okay, because inside the pipe the pressure is less than the atmospheric pressure. So there are chances that outside air can get inside the pipe, and absolute leak proofing is very hard to achieve. Okay, so one disadvantage is that as well, and another is the system is complicated. You are making it a closed system, so when you are dealing with a closed system scenarios, the system is complicated, costly, bulky, and it is not preferred for the aircraft applications. So that is why in aircrafts you generally take an open system gas turbines. Okay, your turbines are open to the ambient. If you have seen at the wings of the blade, wings of the aeroplane. Okay, but in power plants you have closed system gas turbines. Okay. So let me write the disadvantage. The first one is a coolant is used to cool down turbine exhaust before entering the compressor, because if a temperature will be high of the coolant, and if I'm entering the fluid at a very high temperature inside the compressor, it's eventually not going. Compressor is basically a high pressure, high temperature, converting a high pressure, high temperature device. Okay. So if my fluid itself is at a very high temperature, then it's not going to change the temperature much of that uh, refrigerant or the cycle fluid which you are using. Okay. Entering compressor, whereas in case of open cycle gas turbine, atmospheric act as a atmosphere act as a sink and source. And you know that source and sink are basically where the temperature doesn't change in the atmosphere. Next is absolute leak proofing for a cycle. For a cycle is very difficult to achieve. Okay, that is air from outside, or let's say outside air, can enter, since P pressure inside is less than P atmosphere. Okay. Next disadvantage is system is complicated. Costly, bulky, and is not generally preferred for aircraft application. Okay. Now we will introduce one term that is called as back work ratio. Back work ratio. And the notation for this is RBW. Okay. And this is nothing but back work ratio is negative work to that of positive work. So what is the negative work? I mean the work absorbing device. The work which is absorbed by the device, that is your compressor. Work absorbing device. To that of work producing device. And what is work absorbing is basically your compressor, and producing is turbine. Okay. So back work ratio is generally 40 to 60% in gas turbines. Now other definition is work ratio. Work ratio. And this is denoted by RW. So it is nothing but RW is equal to net work to that of positive work. So net work is work done by turbine minus work done by compressor to that of positive work is work done by turbine. So this is 1 minus work done by compressor to that of work done by turbine. And this is nothing but your negative work by positive work, that is your back work ratio. Okay. This is 1 minus RBW, and that is your work ratio. So work ratio can be written as 1 minus back work ratio. Clear? Any doubts? Because we are going to start with the efficiency of simple Brayton cycle. We will derive that. If you have any doubts, please ask. Okay, no doubts. So let's we start with the efficiency of simple Brayton cycle. Efficiency of simple. Why I'm saying simple? Because my working fluid is nothing but air, and it is an air standard assumption I'm going to take. That is air standard assumptions will be, first assumption is that working fluid is air. And it is treated as ideal gas. And its chemical composition is not going to change with the temperature. And its chemical composition doesn't change. Next is value of the Cp, Cv, gamma doesn't change with the temperature. The specific heat constants and the ratio. Value of Cp, Cv, gamma doesn't change with temperature. Okay. Third is you can neglect the kinetic energy and potential energy changes, although they won't be neglected because your combustion chamber, if you have went to or seen a power plant, you can go to Nptel power plant, not Nptel, NTPC power plant, sorry. So if you have seen, if you are nearby to your city is there, you can see that the combustion chamber is somewhere at a different location, turbine is placed at a different location. So eventually there will be datum heads change, pressure, uh, potential energy and kinetic energy changes are going to be there. But we are assuming that for current scenarios that neglecting the kinetic energy and potential energy changes. And you will understand why we are neglecting kinetic energy and potential energy changes. Next, the whole cycle will be a closed cycle. All the individual components are open system. Okay, so I've discussed these closed system, open system, closed cycle, open cycle, everything in detail in my course thermodynamics. If someone is a bit not able to clear about these concepts, you can see in my YouTube channel again at NPTEL I've taught. And again on my YouTube channel at NPTEL with Varnit, you can see in the playlist section the thermodynamics course. But currently let's focus on the course IC engine and gas turbine. That we will be assuming that it will be a closed system analysis. Okay. Fourth, it should be closed system analysis. All processes, yeah, is it isentropic, heat addition, heat rejection, exhaust, all processes are internally reversible. Okay, so there is a two terms are there: external reversibility, internal reversibility. Again, it has been taught in thermodynamics, and I expect that you guys are very familiar with these terms. So all processes are treated to be internally reversible. Okay. Next is both compression and expansion are treated to be isentropic. Both compression and expansion process are isentropic, that is reversible adiabatic. Okay. Next is there won't be, we will be neglecting the pressure losses while passing through the combustion chamber. Although there will be some pressure differences when the heat exchange is happening, okay, as well as when the flow is happening through the duct, which is being connected through various pipes. So pressure losses are there, which is nothing but if you have studied in your fluid mechanics, that is equivalent to FLV square by 2GD. That is your friction factor length of the scale, velocity of the fluid flowing divided by the characteristic length. So again, this is a part of a fluid mechanics. I'm just giving a brief that what are the losses I'm talking about. Again, you can see the course fluid mechanics also I've taught in my previous semester. Okay. If someone is confused with these concepts. So next is your neglecting pressure losses. Passing through combustion, passing through CC and duct connecting various equipments. All right. Now let us see what is the efficiency. After assuming all these assumptions, now you are going to start your derivation. Okay. How we will start? What is the efficiency of any of the system? Efficiency is nothing but output to that of input. You always know whatever output we can get to that of whatever input we provide. What is the output in a turbine? That is your net work which is being produced to that of whatever you have heat supplied, QS. Okay. Now from first law of thermodynamics, net work interaction is in a closed cycle system, in a cyclic process, the net work interaction is your net heat interaction from the first law of thermodynamics. So this can be also written as Q net to that of Q supplied. Okay. Since work done of for a network interaction of a closed cycle is equal to network heat interaction from the closed cycle. Okay. dq is equal to dw. Okay. For a closed cycle. Okay. That's why I've written in the assumption that is it should be a closed system analysis. Closed cycle. Okay. Now what can be net heat interaction? It is nothing but your Q supplied minus Q rejected to that of Q supplied. Again, it can be written as 1 minus Q rejected to that of Q supplied. Okay. Now I can write these Q rejection and supplied in terms of enthalpy as well from steady flow energy equation. Okay. Again, it comes into the thermodynamics that steady flow energy equation is nothing but sum of enthalpy plus kinetic plus potential plus heat is equal to sum of kinetic is equal to basically constant. Okay. Steady flow energy equation, not unsteady flow energy equation. Here the mass flow rate is going to be constant in whole cycle. Okay. So we are dealing with the enthalpy. So net heat interaction will be nothing but your change in the enthalpy of the system. Okay. So this course is basically an application based process course, gas turbines. So you need to have a very basic foundation over the thermodynamics first of all. So if someone is a bit not clear about all these things, I'll prefer that you should go again and check those tutorials. I've taught the whole thermodynamic course in very detail. So heat rejection will be, if you see in this plot, let me make the TS plot once again. Here, temperature entropy plot. So this is temperature, this is entropy. 1 to 2, 2 to 3, 3 to 4, 4 to 1. Close cycle. 1, 2, 3, 4 and 1. So heat is being rejected from 4 to 1 and heat is being supplied from 2 to 3. So if you see, heat rejection is change in enthalpy from 4 to 1. Okay, and heat is being supplied from change in enthalpy 3 minus 2. Okay, heat rejection negative sign, heat supplied positive sign. Okay. So H4 minus H1 to that of H3 minus H2. And for a ideal gas, enthalpy is nothing but function of temperature only. Okay, nothing else. Because we have said that our working fluid is air and it is treated as an ideal gas. So since for ideal gas, that's why those assumptions are very important. Enthalpy is only function of temperature. So we can write that efficiency is nothing but 1 minus Cp times T4 minus T1 to that of Cp time T3 minus T2. Okay, since dH is equal to Cp dt. Okay, so Cp and Cp go cancel out. So this is nothing but 1 minus T4 minus T1 to that of T3 minus T2. Now I'm going to take T1 common from the numerator and T2 common from the denominator. So 1 minus T1, T4 by T1 minus 1 and T2, T3 by T2 minus 1. Okay, this is your equation number 1, let us say, for the efficiency. This is your equation number 1. Now we know that we'll go process by process. So process 1 to 2 is nothing but your isentropic compression in the graph if you see. Isentropic compression. So process 1 to 2 is isentropic compression. So that means PV raised to the power of gamma is equal to constant. And from this we know that T2 by T1, because it's from 1 to 2, can be written as P2 by P1 to the power of gamma minus 1 by gamma. And P2 by P1 is nothing but pressure ratio, higher pressure to that of lower pressure. So it can be written as Rp to the power of x. Let us say x is nothing but your gamma minus 1 by gamma in the short form notation. I'm saying it is x. Okay. This is equation number 2. This is equation number 2. Now let's go to the another process, 3 to 4. Process 3 to 4. Again, it's a isentropic process. If you see in the graph, 3 to 4 is your isentropic expansion. So PV raised to gamma is equal to constant. Again, we can apply the ideal gas law. So T3 by T4 is equal to P3 by P4 to the power of x. Again, gamma minus 1 by gamma. Okay, in the short notation. So I can say that this is equation number 3. Now, if I say the process 2 to 3 and 4 to 1, these are constant pressure process. 2 to 3 and 4 to 1, heat addition and heat rejection at constant pressure. So process 2 to 3, 2 to 3 and 4 to 1 will have 2 to 3 have P2 is equal to P3 and P4 is equal to P1. Okay. So use these terms in this. Okay, write P3 as P2 and P4 as P1. Therefore, use equation 3. Sorry, this is equation 4, let us say. Use equation 4 and 3. Therefore, T3 by T4, this T3 by T4 is equal to P2 by P1 to the power of x. Okay, let us say this is your equation number 5. Now compare your equation number 2 and 5. What was equation number 2? This was equation number 2. T2 by T1 is equal to Rp to the power of x. And this is nothing but again an Rp only. So let me write once again. This is Rp to the power x only again. This is your equation 5. So compare equation 2 and 5. Compare 2 and 5. So it will be 2 was, this is your 5 T3 by T4 and 2 is T2 by T1. So both have Rp to the power of x at the right hand side. So T2 by T1 is equal to T3 by T4 is equal to T3 by T4. So this implies T2 into T4 is equal to T1 into T3. What is the simplest way to remember this? Even terms are multiplied and odd terms are multiplied on the other hand. So T2, T4 multiplied together, T1, T3 multiplied together on the other hand. Okay. Very important, this relation. Okay. Now we know that efficiency is nothing but, so we have seen that T2 by T4 is T3 by T4. Now if you go back in the equation number 1, if you go back in the equation number 1, so that was T4 by T1 and T3 by T2. So let me write here. Can we also write it as T4 by T1? Take this here and take this here. Okay, is equal to T3 by T2. Let us say this is equation number 6. Put equation number 6 in 1. So numerator and denominator is going to cancel out because T4 by T1 is equal to T3 by T2. T4 by T1 is equal to T3 by T2. So this and this is going to cancel out. So you are left with 1 minus T1 by T2 only. Efficiency 1 minus T1 by T2. And if I take T1 downside, so 1 minus 1 by T2 by T1. I can write this way as well. And T2 by T1 is nothing but your Rp to the power of x. This is our T2 by T1 from equation 2. T2 by T1 is Rp to the power of x. This is 1 minus 1 by Rp to the power of x. Hence, equation 2. That is nothing but your 1 minus 1 by Rp to the power of gamma minus 1 by gamma. This is our efficiency of a Brayton cycle. Very important. Okay. Efficiency of the Brayton cycle. Any doubts in understanding this? Please ask. If you have any doubts. We have derived the efficiency of a Brayton cycle. Santosh, Ritesh, do you have any doubts?
No, sir.
No doubts? Clear? Okay. Efficiency of a Brayton cycle is a function of pressure ratio and the index gamma, if you see. Okay. Efficiency of a Brayton cycle is a function of pressure ratio Rp and index gamma. Okay. So if it's a function of this, then eventually we are going to have some plot between efficiency and Rp with gamma variations. Let us see. So let us plot this thing. If I say on y-axis I have efficiency and on x-axis I have pressure ratio. When I say in this formula, if you put Rp to be 1, if my Rp value is 1, so this will be 1 by 1 and it is subtracted from 1. So efficiency is 0 at that scenario. So efficiency is going to be start from 0 when Rp is 1 and it's going to change. So let me make, so it's going to be 1 and it's going to be 0 at the start. So this is this and this. Okay. Now these are the 3 scenarios of different gamma. So this is gamma is equal to 1.3. This is gamma is equal to 1.4. This is gamma is equal to 1.67. So we have seen that with increase in gamma, this whole value decreases and this efficiency increases. Okay. So with increase in gamma, the efficiency is eventually going to increase. So that is why with increase in gamma, you are seeing this. If Rp is equal to 1, then your efficiency will be 0. And with increase in Rp, efficiency is also going to increase. Any doubts? And the expression of efficiency is applicable under both compression and expression processes are, always remember that, when both compression and expansion processes are isentropic, because we have said that the processes are isentropic. So never ever forget that. If the process is not isentropic, you cannot take this expression. So note, the expression of efficiency that is 1 minus 1 by Rp to the power of gamma minus 1 by gamma is applicable when both, only when both compression and expansion both must be, processes are isentropic. If any of the one is not isentropic, it's not going to work. Or even both of them are not isentropic, it's not going to be used at all. Now let us see what will be the effect of pressure ratio on net work output and efficiency. Let us see that. How this Rp is going to affect. Effect of Rp on net work output and efficiency. Let us see. So there is a limit for increasing the pressure ratio. You cannot increase whatever value you want, because with the increase in the pressure, with the help of a compressor which you are using in the turbine, the temperature is also rising up, and any material in this world have some capability to deal before it melts, have a metallurgical limit condition of the turbine blades. You cannot provide so high amount of temperature as well, otherwise your turbine blades are going to melt. So with the increase in pressure ratio, efficiency will increase, but you will observe that net work output is going to decrease. Let us see how. So there is a maximum limit of 1700 Kelvin is imposed due to metallurgical limit condition of turbine blades. With the increase in pressure ratio, efficiency is going to increase. We have seen from the expression above, but net work output increases. How? And for same power output, mass flow rate is going to increase. And if you want to have a higher mass flow rate, the size of the plant, power plant, is going to again increase. This implies large size of plant. Okay. Let us see how, why I am saying all this. Let us make a temperature entropy plot, and you will understand better. So this is your temperature entropy plot. Let us say the maximum limit is till here of achieving a temperature. So T maximum. Okay. When we are saying that our cycle is from 1 to 2, 2 to 3, 3 to 4, and 4 to 1, our closed cycle is like this. Okay. The normal cycle 1 to 2. I can take this cycle till here. This is the maximum temperature limit. 3. 3 to 4 expansion, and 4 to 1 is your exhaust. Okay. This was your original scenario. But now, as you have said, this is your, let us say, cycle number A. Now you have said that you are going to increase the pressure ratio. What do you mean by that? Is that from 1 to 2, you are going to change 1 to 2 dash. You are going to achieve a higher pressure at the 2. So that means your temperature is also going to rise. Okay. So let us say you are taking from 1 to suppose 2 dash here till here. This is 1 to 2. Then again, now you can still not increase more than T maximum, because that's a metallurgical condition. So T max was T3, but you cannot increase more than T3. You cannot go beyond that. So again, if you are doing an isentropic heat, constant pressure heat addition from 2 to 3 from the combustion chamber, so it would be able to possible to do till here only. You cannot go like this. Okay. You are able to do till here, 3 dash. Again, in the metallurgical limits. Okay. You cannot suddenly increase the entropy of the system more. And again, 3 to 4 is your isentropic expansion. Isentropic expansion. That is your 4 dash. And finally, 1. Okay. So if you observe that, this is your cycle B, let us say. Now, if you observe that, the area under the cycle B is much less than the area under cycle A. Okay. So net work is nothing but your net area only. Okay. So area produced is lesser in cycle B compared to cycle A. So net work is going to be decreased. Okay. That is why I said. So we can say that your cycle A was 1 to 2 to 3 to 4, whereas cycle B was 1 to 2 dash to 3 dash to 4 dash. Okay. So the compression ratio in the cycle, sorry, not compression, pressure ratio in the cycle A was P2 by P1, whereas the pressure ratio in the cycle B was P2 dash by P1. Okay. If the compression ratio is high, we have seen that if compression ratio of the B, sorry, pressure ratio of the B is greater than pressure ratio of A, that implies efficiency of cycle B is higher than efficiency of cycle A. Okay. But work net is lesser, because as on increasing the RP, if you are increasing the RP in physical sense, let us understand. This was a mathematical or graphical sense we understood. When you are increasing the RP, that is, you are saying your compressor to produce more amount of, to absorb more amount of work, not produce. So compressor will achieve more amount or absorb more amount of work to increase the pressure to such high state. So your work net is nothing but work turbine minus work compressor. If you are saying my compressor work should increase significantly so that my pressure increases significantly, then your work net, this difference is going to decrease and your work net is going to decrease. Okay. So you have to provide more input work in that scenario. I'll write that. Since on increasing RP, this implies work of compressor has increased. This implies work net is nothing but work by turbine minus work of compressor. So when this is increased, this is going to decrease a lot. Okay. Net work output is going to decrease. That is why there is a need came of an optimum pressure ratio. Okay. We will understand how we will get the optimum pressure ratio also. Till what limit you can increase the pressure ratio so that you get maximum efficiency as well as maximum work output from the cycle. It's not always the efficiency, it should be the balance of both. Okay. Therefore, there was a need of RP optimum. Okay. Need of RP optimum. And when I'm saying that, if I want same work power output, if I'm saying my turbine out power plant is having producing 1000 megawatt of the power, but one plant is working at a higher pressure ratio, another plant is working at a lower pressure ratio. So which one is working at a higher pressure ratio? The work net is going to produce lesser. The power net is nothing but mass flow rate into work net. Okay. If my work net is less with a higher pressure ratio, to maintain the same 1000 megawatt of energy from the turbine or a power plant, I need to increase the mass flow rate. And if I'm increasing the mass flow rate, eventually my system should be having a larger dimension, larger space to have. It will be a bulkier system. Okay. So we can say that mass flow rate for same power output will be greater in mass flow rate of B. Okay, because your work net is decreased in case of B. All right. Clear or any doubts? Please ask. No doubts? Now let us derive the optimum pressure ratio. If there was a need of optimum pressure ratio for maximum work output, let us derive optimum pressure ratio for maximum work output. Okay. So work net is nothing but work turbine minus work compressor. What is work by turbine? S3 minus H4, because turbine is from 3 to 4, if you see, and work by compressor is 2 to 1. Okay, minus H2 minus H1, and it can be written as Cp T3 minus T4 minus T2 minus plus T1. Okay, if you simplify it, we know that T1 is your lower temperature and T3 is your maximum temperature, and these are your constant values. Okay, constant. Okay. This is your lower T lower, and this is T max, that is your T max, and this was equal to T3 dash as well. Okay, these are constant values. Also, we know that we have seen that product of even is equal to product of odd. So from here we can write T2 in terms of T1 T3 by T4. Okay, so put this T2 here, that will be work net Cp times T3 minus T4 minus T1 T3 by T4 plus T1. Okay, for work to be maximum, the differential of the mathematical term of with respect to T4 should be 0. Okay, net work, that is for maximum work output, for maximum work output. Okay, if you differentiate the above equation with respect to T4, you are going to get T1 T3 by T4 square is equal to 1. So this implies T4 is equal to under root of T1 T3, and T4 is equal to again T2. Okay, T4 and T2 are going to be same. All right, because if you put here T4 as under root of T1 T3, so it will be T1 T3 by under root of T1 T3. That will be same. I think you can get confused. I'll write this step also. Since T2 is T1 T3 by T4, put this here, your T2 will also come out to be root of T1 T3. Now put all these values T2, T4, T1 in the work max net. Therefore work maximum net is nothing but Cp times T3 minus root of T1 T3 minus root of T1 T3 plus T1. Okay. This is Cp times T3 minus 2 T root of T1 T3 plus T1. So can I write it as root of T3 square root of T1 square? So this is A minus B whole formula. A square minus B square is equal to A square minus 2AB plus B square. A minus B whole square formula. Okay, A square minus A square plus B square minus 2AB. Where T3 is your higher, T1 is your lower, as we have written here. T1 is lower, T3 is maximum, and these are constant values. They are not going to change. So that is Cp times root of T3 minus root of T1 whole square, and that is nothing but your work mix net is Cp times under root T higher minus under root of T lower whole square. This is your net work maximum obtained. But we have to get the RP optimum. We have not got the RP optimum. We have net work maximum. Am I audible? Hello.
Audible, audible.
So we have got the net work maximum, but we have to get the pressure ratio. So T2 by T1 is nothing but your P2 by P1 to the power of gamma minus 1 by gamma. So that implies P2 by P1 is equal to T2 by T1, and take this gamma that side, gamma by gamma minus 1. And this is your pressure ratio only. So this implies Rp is equal to T2 can be written as under root of T1 T3. We have just seen by T1 to the power of gamma upon gamma minus 1. So this implies your Rp is root of T3 by T1 to the power of gamma upon gamma minus 1. And T3 is higher, T2 is lower. So this can be written as Rp is equal to T3 by T1 to the power of gamma by 2 times gamma minus 1. Under root I have written as 1 by 2. This is nothing but your T higher by T lower to the power of gamma to that of 2 times gamma minus 1. This is your optimum Rp in terms of higher and lower. These are your values, constant values. Okay, T higher and T lower are constant fixed. All right, this, you got your optimum RP as well, for which your net work maximum is this much in terms of higher and lower. Okay. Any doubts? No doubts. So I think we can end this session here. So those who have not watched the tutorials, have missed any of the tutorials, all of these recordings are available. And the link of the recordings come from the NPTEL team. Those students who have registered for the course, you can see there. Every week the NPTEL team shares the link. As well as if you are new, you don't get the link or something else is the issue. You can directly check out my videos, these recordings, which are available on my YouTube channel, that is NPTEL with Varnit. Okay. So in each, there is a playlist section for the corresponding course, ice engine and gas turbine. In each playlist, there are a set of videos, week 1, 2, 3, and so on. And each video description, you will see a link of Google Drive where you can see the PDF of these notes. Okay. And I hope everyone is like continuous and regular to their assignments, doing the assignments, watching the lecture videos by the professor, as well as these tutorials. And I expect that everyone should be there joining continuously. And almost we are towards the end of our tutorials and the course. It's 8th week which has been completed. The course is of 12 weeks. Okay. So I'll see you next Tuesday, same time, 6 to 8 p.m. All right. So we can end the session. Thank you. If you have any doubts, you can ask me.